Okay, walk with me through Chapter 11, Wit and Wit, beginning on page 225. I told you that we would talk about one and two tail tests and some other things too. A one-tail test is, I'm sorry, well, I'll start with the two. Let's do it that way. A two-tail test asks a question like, is there a difference? And two-tail test has to do with the normal curve. And remember, I found that plus or minus 1.96 as our boundaries between common and rare. Where if I ask, is there a difference? The difference can be one of two ways. If I'm comparing A and B, A can be higher than B, or A can be lower than B. That's why it's called the two-tail test. If I just ask, is there a difference, and I don't specify a direction, a two-tail test is also called non-directional, because I don't say which way the direction has to go. I don't say that one is higher or lower than another. I just say simply, are they different? And they can be different either on the high side or on the low side. And two-tail tests were, like I say, what we were doing with those previous examples. A one-tail test it is also called directional. An example of that, comparing A and B again, would ask, is A higher than B? Not just are A and B different, is that not just is A different than B, is A higher than B? I've specified a direction for the difference I'm looking at. If A is 82 and B is 86, and let's say that we found that that is a significant difference. Well, let's just look at the raw numbers. Is A different than B? Yes. In a two-tail comparison, the answer would be yes. Is A higher than B? No. So in a one-tail test, and I'm going to add one more phrase here, a one-tail test, upper tail critical, because I asked the question higher, the answer is no. Another one-tail test, or another one-tail question would be, is A lower than B? The answer is no here. The answer is yes here. While the first part where I'm asking higher, I'm asking on the high side, that's the upper tail. So that's upper tail critical. If I'm asking lower, being on the low side, that would be then, I bet you know what the answer is. Lower tail critical. But really, upper and lower tail doesn't make much of a difference because remember the normal curve is symmetrical. So the answer is going to be, you're going to look at the same numbers in terms of comparing. So directional means I'm using a word like higher or lower. Non-directional, I'm just using the word different. And that's the difference essentially between a one-tailed test, which is directional, and a two-tailed test is non-directional. And like the great philosopher Forrest Gump said, that's about all I have to say about that right now. We'll specify the kinds as we talk about different questions. So if I ask, here's the difference. Let me give you an example. Walk through an example of the difference. Remember a minute ago, we asked the question: is 533 different than 500? In the previous example, comparing my 100 students' SAT average of 500 with the national average of 500, and we said yes, it is. I could also, and we compared, we got a Z of 3, and we said that's higher, or that's outside. I'm going to say it this way because you'll see why I'm going to in a minute. That's outside that plus or minus 1.96. At the 0.05 level of significance, yeah, there's a difference. What if I say is 533 higher than 500? I still get a Z of 3. But my question here looks like I don't care about either. I care about one direction and not the other. I only care about the high side. I'm going to get the same answer because the number's strong enough, but I only care about the upper tail critical. That means all 5% is up there. My critical value for the just difference question, the non-directional question, was plus or minus 1.96. What is the critical value for a one-tail test? Nobody's looking in your book yet. Okay, look at the table. Again, table on page 530, 531, table A. And I want to see that entire 5% on the upper tail. So I'm going to look at a C column of 0.05 or a B column of 0.95. I'm sorry, not 0.95, 0.45. You're looking at, well, we tend to want to err on the conservative side, so we're going to look for a higher critical value. We're actually going to look at 1.65. Did I get that right? .45 in the B column, because if it was on the low side, it would be it would be more than 5% away from it. Yeah. So we're going to look at 1.66, but still, because again Z is still larger than 1.65, the answer is still yes. 5.33 is higher than 500. So with a one-tail test, I'm going to compare the Z-score with 1.65 at the 0.05 level of significance, because that 5% is no longer spread out on the left and the right. It's just all pushed together on one end or the other. Now, It could be that, again, my 533 is going to be somewhere up here. But again, it could be, it's possible, barely possible, that the sample was so skewed that I just happened to get lucky and pick the good students. And by the way, this is a danger when you compare SAT scores between states. What are the high-performing SAT states? I think something like, I want to say Montana was the highest a couple of years ago. The lowest tend to be like South Carolina. Well, is it because, again, let's talk about interpreting properly, is it because the South Carolina students are dumber than the Montana? And the answer is not necessarily. Could be, but not necessarily. In Montana or whatever state, the best students take the SAT. In South Carolina, everybody takes it. So of course, when everybody takes it, it's gonna be less than the best. So be careful of making these kinds of comparisons from one situation to the other, because the difference in the environment is probably more than just the test scores themselves. So again, grain of salt. But now, it's possible that, okay, I am rejecting the null hypothesis. I'm saying that my SAT scores are higher than the national average. I could be wrong in saying that. And we've talked about what that's called. What have I made if I make an incorrect assumption? I made a mistake. Okay, what's the statistic? We used it about 50 times tonight already. I've made an error. I've made an error. Let's talk a little bit more about classifications of errors. If you look on page 236, I can make, I'm looking at the null hypothesis. The null hypothesis is either true or it's false. And I either retain, meaning I don't reject, or I reject. I've got four possibilities here. If the null hypothesis is true, and I say it's true, that means have I done the right thing? The null hypothesis is true, and I say, hey, the null hypothesis is true, I'm going to keep it. I'm not going to reject it. If I do this, is that the right thing? It's true, I say it's true. Have I done the right thing? No. Just forget about the don't. A statement, I retain a true statement. Whether it's positive or negative doesn't matter. It's a true statement. I've done the right thing here. What if the statement is false? Yes, a null statement, but the statement itself is false. And I say, hey, that's false. I reject a false statement. I've done the right thing. Now, what if I reject the null hypothesis and I should not have? I say it's in the rare area, but it really was not. I've done the wrong thing. That's an error. Specifically, and I'm not going to venture to hold you accountable for learning which is which too much, but follow me on this because you'll see why I'm doing what I'm doing. This is called a type 1 error. A type 1 error when you reject the null hypothesis, meaning I say there's a significant difference and there's really not. That's a type 1 error. On the other hand, I bet you know what this is. The null hypothesis is false, but I don't reject it. I bet you know what kind of error that is. That's a type 2 error. Now, so in other words, there really is a difference, but I say that there's not. Now, let's say I'm looking at this new math curriculum, and it's going to cost $20 million. So it's kind of a big deal. and I'm comparing Group A, taught by the old tried and true, same old stuff, and Group B is the new whiz bang stuff. If I make a type 1 error, I say essentially there's a difference when there's not. We're going to buy into this $20 million program. That's the result of a type 1 error. On the other hand, if there really is a difference, but I say we're not, so we're not going to buy into the $20 million program, I've made a type 2 error. I don't spend the $20 million, which is worse. In other words, is the sin of omission or commission worse? Is it better to spend it when you shouldn't or not spend it when you should? Generally, yeah, neither is good. Generally, a type 1 error is considered to be the most serious. That would cause me to make a change I should not make. A type 2 error would cause me not to make a change I should make. We tend to err on the side of saying, well, if we're not sure we should do something, let's not. And that's probably just kind of good common sense overall. So a type 1 error is considered more serious. And the chance of a type 1 error, in our case, we are willing to put up with, ooh, you'll see this is familiar, a 0.05 chance of making a type 1 error. That means we're going to be very conservative in drawing results that cause us to make any kind of changes. Now, I could always avoid a type 1 error by saying, I'm never going to make a change. So I could avoid a type 1 error by never rejecting the null. Well, that's not very helpful, is it? Hey, you'll never make a type 1 error. I want to see if there's a difference. There's not, because I'm just going to say that. That's not very helpful. On the other hand, how could we always avoid a type 2 error? By never doing it. Never making it. By never rejecting, always making the change. By golly, I'm not sure if we should do it or not, but we're going to not make the mistake of not doing it. What? Type 2 is when you don't do. Type 2 is when you. Let me shave off the double negatives. Type 2 is when you don't do something you should. Okay, type 2, I've got my control group, my experimental group. The question was to use the math example in terms of what a type 2 error would look like. I've got my control experimental group, and I am not rejecting the null that there's a difference. Follow me, sort of? I don't know if I should change or not. So I could avoid type 2 error by just, no, the other way around, always changing. Remember, doing something you're not sure about is what's serious. We're going to be very conservative in making a change. Again, I'm not going to hold you accountable, just understand it works. I want you to understand it works both ways, and our alpha level, our level of significance of 0.05 is why we use that to control for a type 1 error. That's more likely to kind of keep us from doing something we're not supposed to do. That's my main point. Type 2 would be not making a change when you're supposed to. Yes, correct. Yes. And I could avoid a type 2 error by always making a change. I could avoid a type 1 error by never making a change. Not very helpful. You mentioned you were skimming through the chapter and you saw something called beta. That had to do with beta has to do with a type 2 error. We don't deal with that much. There's also something related to beta that is power, which is 1 minus beta, that the probability of not making a type 2 error. But I'm mainly concerned with type 1 errors, and that has to do with our levels of significance, 0.05, which is also called an alpha level. Alpha level. We generally look at a 0.05 level of significance. That means we want our probability of being wrong, our probability of making a type 1 error less than 0.05. The 0.05 is also called the alpha level. Alpha level. And that's kind of, well, it's a Greek A, Greek alpha. It's kind of a fat fish symbol. Question, the SAT is not preferred in the South. Well, it depends on the state. North Carolina typically is an SAT state. Tennessee is more of an ACT state. So, and South Carolina is an SAT state too. So you're right. It does vary state to state, but and there is some regional pattern to it, but not strictly South and non-South. But yeah, it does matter where you are. Comment was made. Thanks. Other questions, comments about, again, I'm more concerned with type 1 errors, which a type 1 error says that you're saying there's a difference when there's not a difference. It tends to lead toward making changes that you should not make. If I'm not sure I want to spend this $20 million, I better be dang sure before I do. If I'm really not sure, I probably better not do it. I probably better not. Yeah. Also, most colleges will take either one, and there are conversion formulas that will equate a particular. Well, we've already been over the conversion factors, how that works. The way you compare is that most colleges, up to individual colleges or university, that will take either one. So yeah, but you're right though. It does one. Some states emphasize one over the other. Okay, so we're willing to put up with if we reject the null. We're willing to put up with a 5% chance that we've incorrectly done that we should not have rejected the null. Let me shave them double negatives off again. If I say there's a significant difference, I'm willing to put up with up to a 5% chance of that statement being wrong. Now let's expand this just a little bit here. What if I have a bunch of null hypotheses, and I reject them all? Let's say I've got 20. I'm probably wrong on one of them, because that's what 0.05 is. 0.05 means a 1 out of 20 chance. So the more you have, the more you're likely to be wrong on something. The more you say, the more more likely you are to say something wrong. Believe me, I know that. We don't talk about levels of significance with type 2 necessarily. And matter of fact, we're not going to talk much about type 2 at all, at least not right here. But my point is what kind of error, this 0.05 that we keep talking about, what kind of mistake that's tied to? What being wrong about that would mean in terms of what we're doing wrong or we conclude wrong. There's also something in your chapter that if you're skimming through the chapter that I'm not going to talk about now, but I'll talk about the second half of the course, but I'll just name what it is. It's something called effect size. Effect size, E-F-F-E-C-T. It has to do, again, I'll just give you a real quick, very incomplete, inadequate explanation. Yeah, it's different from finding a significant difference. It's a matter of if there's a significant difference. I like the way one of my students put it one time. How significant is the significance? I mean, you could have a significant difference, but it may not really mean anything in the real world. The effect size has to do with how big it, okay, you're saying, yeah, it's a big deal. Okay, well, how big a deal is it then? So that's all I want to say about that for now. Yeah, effect sizes are calculated. We'll talk about how they're calculated when we talk about other kind of inferential statistics in the second half of the course. Okay, so just a little bit about 1 and 2 tail tests and types of errors. Any questions about that? This is kind of a short session. Yeah, when it was 1 tail. Okay. The yeah, the statement was a true statement. Yes, the cutoff point, the boundary between common and rare, was 1.65. Again, for the .05 level. That account, yes, right, because it's only one. We're only worried about one tail. It's just directional. There's not one on the other side. So for a two-tail test, keep in mind, okay, two-tail test. If I'm looking at 5%, I'm looking at 2.5% being here, and 2.5% being here, and that's plus and minus 1.96. If I'm looking at a one-tail test, I'm looking at the entire 5% being just on one end, and that means my borderline between common and rare is 1.65. My bump point, as you said. Okay. Y'all have your own language here. Well, the 1.65 has to be further to the left because I've got more under the area to the right of it. So 1.65 has to be smaller than 1.96. Yeah, because I'm shoving. I'm going all the. I'm only going out to 5% here. I'm going all the way out to where there's only 2.5% left here. So I go out further for the two-tailed critical value. Oh, really? I said something right. Amazing. Okay. Okay. All right.